Hi, everybody. Welcome back. So I'm going to take some time here to talk about some of the stuff we covered a little bit this morning. There's been a lot of progress with neural models and natural language processing, but there are still a few gaps. We're going to explore a little bit what those gaps are and talk about both practical ways as well as some of the newer academic research in being able to address these things. I'm Catherine Havasi. I'm a research scientist at the MIT Media Lab. I'm also known for running a project called Open Mind Common Sense, or ConceptNet, which I'll talk a little bit about as we walk through all of this talk. Okay, so the morning set up the problem here pretty thoroughly. There is a lot of progress in natural language processing and neural models, but those neural models don't seem to think about the world like we do. They tend to have very different reactions to things. When they fail differently than people do. And this is one of those things that becomes sort of a big problem for NLP and for believability and user interface design and pretty much everything else that we could want to do with computing. It's also quite funny often when it goes wrong. And one of the reasons it's funny is because things that are funny are things that tend to fail in ways people don't, or that push the expectations of how we think about the world. We tend to be very good at learning things quickly, which is definitely not something that's true of neural models. We tend to be very good at learning things with few information. We make really good guesses. So how do we do this kind of thing? How do we make it happen? One of the big components of how we make these things work is something called common sense. Now, if you're not familiar with this is actually a technical term. It basically means things we know about the world, the basic world knowledge that underlies things. We tend not to write these things down. If I drop this clicker, it would hit the floor of the stage, but nobody ever says that. Nobody ever talks about what happens if you would drop a water bottle, or the fact that the table is actually, if you put something on a table, the object's not going to go through the table. These are all things we learn really early. So unlike domain knowledge like medical or financial services, it's harder to learn that stuff from text. Now, I'm sitting here with a giraffe behind me, and one of the reasons for that is by now you've probably thought a little bit about what would happen if a giraffe showed up in this auditorium. Is the ceiling quite tall enough? Would the giraffe be happy here? Probably. But it's one of those things that we've never thought of before. You don't walk into your average room and think about giraffes, but every one of us had about the same picture in our head with about the same giraffe, and trying to see whether or not it had clearance in the room. So that illustrates sort of the two parts of common sense. One of them is the facts we all know about the world, the prototypical giraffe we all have in our heads. And the flip side of that, the ability to reason on that information with that giraffe. So we're able to understand what would happen if the giraffe goes in the room, and we all have about the same understanding. The flip side of the common sense is how we reason and how we work with common sense. The linguistic philosopher George Lakoff talks a lot about how we work to understand complicated concepts by making analogies back to simple concepts. Information is a really good way we think about this. You know, we talk about information as flow. We talk about data almost like it's water. You know, if you work at a large company, you probably have a data lake. A couple of years ago, there was a joke going around the internet about the internet being a series of tubes. And all of these things sort of indicate how we think about and how we contextualize a big abstract concept like data. So we started collecting common sense from volunteers on the internet, possibly some of you, in the late 90s. It was one of the first, if not the first, crowdsourced AI training effort, initially to get intent for search. And over the years, we built knowledge graph models that we make freely available online in 73 different languages, including Hebrew and most of the languages I hope you folks work in. And those linked models between languages have been a resource for different kinds of machine learning. We definitely do a lot of different languages that you may be running into. Some of the projects were done through crowdsourcing, some of them are done through a partnership with the folks who you think of as the people who make Wikipedia. But natural language processing has changed a lot since we started the project 20 years ago. In 2013, Google popularized a type of machine learning that most of you know as word embeddings or using deep learning for language, or the beginning of that. And things kind of changed for us. Most people here probably know how these things work, but if you don't, you can really think about this as distributional semantics, as understanding how a word works in context with the other words and making sense of it that way. This tends to have a couple predictable faults, one of which is that words that appear in sentences in similar places but have very different meanings are often mistaken for each other. In my world, it's things like the Red Sox and the Yankees, which are baseball teams, one of which from my native Boston that I'm a fan of, and the other one of which is sort of the rival of that one. Or things like middle school and high school, or other sorts of words. And so enter using common sense to fix this problem. We know these things. And so a technique was developed called retrofitting that basically allowed us to make changes to the embedding. Back then, we understood enough of how these models work that we were able to go inside and make edits to the model after it was trained so that we could fix this lack of common sense problem. And so if you don't know how this works, one quick thing, as we go through the talk, there's going to be little technical references on the bottom. If you want to get into more depth than what I'm doing, please take a look at that. And there'll be a big slide at the end with lots and lots of links. So basically, if you can think about all the concepts in the world being little star points, and the representation that comes out of a word embedding being a big galaxy, what we're doing when we retrofit is we pull points together that are related to each other in the knowledge graph, and we push them apart if we know there's something like an antonym in the knowledge graph. And this worked really, really well when embeddings were the state of the art. In fact, in the 2018 SEMeval, over half the benchmark competitions for NLP used a technique like this to become state of the art, whereas the previous year there had only been one. So it was really trending up, and other areas of machine learning started picking it up. We saw advances in this in multimodal learning, and honestly in things as crazy as robotics. Around that time, we started putting out a new software package, which we still do, called Number Batch, which is a freely available 73-language retrofitted embedding set. It's open source, open data. You can go use it right now to be able to add common sense into some kinds of NLP. We do it by basically combining together an ensemble of different types of learning methods. We then retrofit ConceptNet into each one of those, join them together, reduce it a little bit so it's not too big, and then try to debias, which is a whole different talk, debiasing NLP. And then we put that together and release it. And this is great. And then things changed for NLP maybe about 1.5 to 2 years ago. We started coming out with, what we think of as the Sesame Street or the transformer models, things like BERT and Elmo and Roberta and the newer models. And these models were fundamentally very different than the embeddings models that came before them. It was really hard to just reach inside one of these models and make changes the same way we were before to add common sense back. And the performance of these models was much better than the performance of things like Word2Vec or Glove or the other models we were using before. So and within these models, even though we don't know how they work, there's a whole new subfield of NLP that we like to jokingly call BERTology, where we get inside these models and we try to figure out what's going on. Why is it doing what it's doing? And although the answer is still we don't always know, there's a lot of really interesting things going on. Incidentally, if you're interested in this, there was a great paper published 1.5 days ago on this from Anna Rubczycki's lab at UMass. But basically what's going on, we've seen things that look like they could be parse trees inside BERT. We've seen things that look like they could be semantic models inside BERT. So does that mean that there's a knowledge graph inside BERT? And if so, why are we collecting all this common sense? Is it still something that's helpful, and is it still something that's useful? And as we move into the era of transformers, I think the big question is, what is the place for structured knowledge? What is the place for regular knowledge graphs and ontology models in this paradigm? And to really attack this problem, we want to start out by thinking about how good is BERT at actually doing common sense. Early work at this point, like probably an earlier speaker brought up, a lot of good work starts being done by the Allen Institute, which is both here in Tel Aviv and their headquarters out in Seattle in the US. And this is one of those papers. Really early work showed that BERT made a pretty dramatic improvement in different types of common sense. Things like encyclopedic common sense or functional common sense. It was really night and day with BERT, between that and something like a glove or a word2vec. But more modern papers have started exposing a lot of problems, and some of those were covered this morning as well. This is a newer reference that came out a couple weeks ago at AAAI. Basically, what ends up happening is an adversarial attack was done against BERT, where it comes up with paraphrases of different words inside a wide variety of tasks, everything from classification to things like movie reviews. And we find that these paraphrases, which are things, there's a couple of them up there, I'll give you one of them right now. The characters cast in impossibly contrived situations are totally estranged from reality, which is the kind of thing in a movie that maybe you don't want to see. If we rewrite that to the characters cast in impossibly engineered circumstances are fully estranged from reality, none of you would have any trouble telling the difference between those two sentences, but models like BERT do have a huge issue. And that really makes us question what's going on inside them and whether or not the kinds of things that we're doing can make a big difference. So really what I see is this synergy that's developing, much like some of the speakers this morning, between knowledge graphs and structured knowledge and something like BERT. A knowledge base can add a lot of information to a contextual transformer. It can add the robustness back in that we've seen, and we'll talk about ways to fix the is BERT robust study in a second. And it can also add really important things like explainability. These models are black boxes. We don't really know how they work. I, for one, think that's not going to fly in the long term, especially if you're deploying in all kinds of different environments. So being able to cast back into a knowledge graph or a structured knowledge resource holds a lot of promise for fixing some of these explainability problems. It can also help generalization in models, so helping models that are trained to do one thing do another thing. So this is transfer learning or fine-tuning. On the flip side, transformers can help knowledge graphs and all of this kind of structured knowledge engineering by helping to increase the coverage and the connectedness in those knowledge graphs, as well as helping them specialize to domains, and perhaps getting closer and closer to the hit button extract knowledge graph sort of dream of parts of NLP. So some quick work that I'm going to go through very quickly in this area recently that's been of interest include exactly reversing the paraphrase sort of attack I've talked earlier and using it again to teach the knowledge graph. So can we take something that we know is true from a knowledge graph and train using paraphrases to try to get, and this was originally done on Elmo, it would be very interesting to do it on a more modern transformer, to be able to get that kind of information back in the system. We don't have a structural way like we did with retrofitting at the moment to put the knowledge directly inside the model yet, but there are ways to sort of trick it and ways to make it work. This is one of them. This paper is actually the workhorse. If you need to put common sense in a neural model today, this is what I would recommend. The way these things learn involve something called fine-tuning, which is a type of transfer learning where you continue to train on a particular data set. So what you can do is take your knowledge graph, read a corpus like Wikipedia, find sentences inside Wikipedia that support the stuff in your knowledge graph, the relations, and then just keep fine-tuning on that. So you're essentially emphasizing to the transformer that these type of relations are important and you didn't weight them well enough when you trained the first time. And that's shown some interesting results as well. There have been some papers in other areas. I'm not going to talk in depth to this. If you want to talk about this, I'd love to talk in the break. But this paper is the closest that we've seen to adding common sense structurally back into these kinds of knowledge graphs. And there's a lot of work ongoing to see whether or not we can apply these techniques. We've been doing some work in regular embeddings to try to come up with ways that we can possibly attack this combination problem. One of the things that we've been doing is training to use a GAN to basically watch somebody retrofit and embedding, to watch the computer retrofit and embedding, and try to understand whether or not that retrofitted embedding, to try to reproduce that retrofitted embedding. This solves a pretty key problem, which is if you're retrofitting, we can take the word dog, which we have in our knowledge graph, and we know all about dog, and we can move it to the right place inside the model, and that's great. But anybody who spends any time on the internet probably has run into the word doggo, which is a very cute little dog on Twitter. And what's going to happen is we're going to move dog, but we're not going to move doggo because nobody bothered to put, and that's probably a good idea actually, nobody put the word doggo in our knowledge graph. Right, so we're not going to retrofit it in. But what the GAN will do is be able to learn that the word doggo should also be moved to the place the word dog was. And from that, we're able to build a better, more automated process for retrofitting. And there's ongoing work that we have under review on trying to see whether or not we can use this to do other kinds of transformations as well to spaces. And we can flip it around and use transformers to build knowledge graphs. If you have been working in building knowledge graphs a long time, something that drives you nuts is the fact that some of the knowledge graph is much sparser than other of the knowledge graph. Meaning that there's a lot more information about mug than there is about brushing your teeth. That's just something that happens when you crowdsource. And so we can use transformers to fix that. And we can also use transformers to build new candidates. In the same way you would generate newspaper articles about unicorns in the Andes, you can generate fake statements in a knowledge graph and then see if they fit back in. And that's also very interesting. The flip side of this, and you're saying, well, this was all great, that's very modern research, but I have real problems that I need to deploy, and I'm never going to be able to deploy a BERT to do that. It's just not stable enough, and it's a black box. So how can I make these things work together in a way that's a little bit more deployable today? And one of those things is to take a look at embeddings models and other sorts of information and say, how does something like common sense help us generalize or learn domains? Because when pre-trained models are great, they often have issues going into something like a domain or a different language or a particular expertise level, because the language that's being used by the customers, your end users, or inside your organization is very different than the language that was trained on in the model. And so what you end up with is words having different meanings. You know, you could be an extreme sneaker company talking about the fact that bad means good because people are saying, you know, these sneakers are really bad, and by that they mean these sneakers are really good. Or you could have all kinds of different other things, where in healthcare there's vocabulary and jargon. So that's domain adaptation. It becomes very important. And often when people try to do NLP commercially, one of the issues that they have is trying to do domain adaptation, not doing domain adaptation. It doesn't work. They conclude NLP is bad, and we don't like to see that. We did a startup in this, 10 years ago, 2010. It's still going, called Luminoso. I wouldn't think of it as a startup as much anymore, that looked into some of this. But there's been a lot of other information and transfer learning. People want to take pictures of this? Okay, I should let that happen. People at Luminoso folks would definitely want me to let that happen. So also there's been new models that have come out that have done different kinds of transfer. How do we build a general model and have it be able to attack and transfer to different problems? Maybe last week, was it even last week? Google came out with a new model called T5 that's specifically for this. They have a lot of interesting information on it. And there are a couple of other places you can download or try to use transfer learning. Most of them are from more modern transformers because it becomes harder to transfer learn on embeddings, but that's sort of why we built the company. But one of the problems that we have is that we can also see in conversational AI that these transformers tend to fall down because they don't have common sense. I used the unk example in the very beginning when I was talking about this, but anytime you have a model try to explain what's going on in the picture, it will come up with these ridiculous explanations that defy common sense. So that's another place where even though we can't put an evaluation on it, we know that this is an issue. If you're out here and you want to be implementing these things, something I would recommend is that there's a lot of different models and code available on Hugging Face's website that's sort of pre-shrink wrapped, easy to use transformers. It's a good place to get started. And so if you want a practical way of using these things, that becomes very important. The speaker from Microsoft this morning quickly mentioned distilling, which is a very important thing you can do after you fine-tune to make your model smaller and more focused. You can do that there as well. So what we're doing now is actually trying to work on applying common sense to conversations. And the thing that we realized is that when we communicate via chatbot right now, we're basically, industrial chatbots are designed to get people off the phone as fast as possible, which is important for customer experience because the alignment is the same between the software, the company that's deploying the chatbot, and the person that's using the chatbot. They all want their problem to go away as fast as possible, but chatbots tend to fail when that's reversed. So we're looking for ways to build chatbots that are not sort of chit-chat conversational chatbots, like I think that's been covered a couple of times, but are also not CX chatbots where you want to get people off the phone, and we're finding that common sense is very useful for that as well. So hopefully that's been interesting. If you want to play around with ConceptNet, even if you're not sure if you want to use it, you can browse at conceptnet.io. That is just a browsable version of what we're doing. It has the connections between all the different languages and the different relations that we have freely available. We have an API. We host it. And we have, duplicity, and I'm not a ops person, so we don't go down, right? We have a whole lot of things that are designed by people who actually do this stuff to not go down. So you can rely on, use the ConceptNet API. You can actually download the entire package as well. But let me warn you, it's really big. So you might not want to do that. You might want to play around with the API first and then sort of set something up. We have a users group and a users Slack and all kinds of things as well. So this is the eye chart slide. I talked about a lot of things very briefly because all these talks are very short. But if you want to learn more, let me get out of the way. These are all kinds of great places to get started, including the talks on retrofitting, how to get number batch, and places to go to learn more about sort of the evolution between these types of NLP. Okay, looks like we're good. And with that, I want to thank you. It's been fun coming here and talking to all of you. And if you have any other questions, I am happy to be available at the break. And if you didn't get the list or if you have other questions, do give me an email, and I'd be happy to help you find things. Okay, thank you.